example, let's take n equal to 10, then n big would be 10 to the power 10, which is 1024, and the square root of n will be 32. And suppose that we run Shor's algorithm and we get y equal to 139. So we have this value, 139, divided by 1024, and we search for some fraction near it in this proximity of it, which has the denominator less than 32. So how we do it? We revert this fraction like this. Which equals to 7 here plus 51 divided by 139. And this is our first estimation, 1/7. It is close to this fraction, and if it is not close enough, we continue this. So if 1/7 does not meet our requirement to be close enough to our original fraction, we go further. 7 plus 1 divided by 139 divided by 51, which is 7 plus 1 divided by 2 and plus 37 divided by 51. So our next estimation is this. And if we multiply both numerator and denominator by 2, we will get the second estimation, 2 divided by 15, which is closer to this original fraction. And still, it has denominator less than 32. If it does not fit, if it's still not close enough, we continue this infinite fraction. And the next value we will get 3 divided by 22, which I think meet our conditions. And if it don't, the next value would be 8 divided by 59, which is very close to the original fraction, but it does not meet the condition of the denominator to be less than 32. And if it happens, we may conclude that the y that we have measured is not a good y. Okay, on this slide here, you see the implementation of Shor's algorithm on the quantum computer simulator, link to which you can find in the materials for the course. I can write it right here. It's http://qc quantum computer simulator app spot.com. Okay, and P and Q are chosen here like 3 and 5. So the product is 15 here, and we randomly choose 7 as this A, so the function fa is function f7 here. And we see the implementation of QFT we already discussed before on this week, so it is QFT. And this is our UF operator. Here we have a Damar. And how to implement the UF operator, you will understand if you do the exercises for this week. So probably that's all this with this example, and you can try it yourself by this on this internet address, or you can try it for different numbers of numbers p and q, and you will need to implement this separator UF differently. Maybe you will try more qubits, so you would have to implement this quantum Fourier transform differently. So good luck with that. Well, to conclude, imagine we have this big composite number, the product of two big primes, and we want to factor it. So we choose some random number a, we define this function fa, and we search for its period. We employ Shor's algorithm, and we get some y with probability almost to 1/2 it is good y. So we search for this k divided by r in the proximity of this value, in a short proximity. And if we find, then we try to use it as a period. If it does not fit, we can think that it is one of the denominators of this period. So we have to run Shor's algorithm many times and to recombine these values that we get. And we try to build the value of period. And finally, when we succeed, this period may happen to be odd, and we have to start all over. All this seems a little bit time consuming, but it's not if compared to the classical approach to this problem, because for the Shor's algorithm, even if we have to run it several times, maybe many times, it is only n squared, where n is number of bits, and all known classical algorithms to this time are over polynomial at this parameter. So for big N, for classical computing, this problem is untractable. And for quantum computation, it's just a little bit time consuming. So what I'm trying to say is that Shor's algorithm provides us with exponential speed up over the classical computing for this task of factoring and period finding. I want to wish you good luck with your control test, and I hope to see you next week. Bye.